Hello. So only Dan is here. Hi, Dan. Hello. Hello. Hi, Dan. Okay, you're typing. All right. Okay, so I see that you're the only one here now. So let's wait for 2 minutes. Maybe someone is gonna join us because I was accessing Zoom through the link, and then I realized, okay, it's easier through the app. Through the link, I was seeing like 3 people. So let me see, maybe we have some confusion with link versus app. Okay, so let me just wait 2 minutes and then we will start. Okay, so let's start. So today we're gonna have lecture of week 3. And as you know, like you have it on Sakai, all the lectures by tab, like we have the weeks. So if you just click on week 3, you will get to this site where you see all the readings that you have to do for this week. And the first, I would say the first 4 weeks for the readings, I have some selected sections. So it's not like a full section 6 or full section 7, or the previous week we had some sections from chapter 4, some sections from chapter 5. But then later on, starting week 5, we would have like the readings are just chapters. So for this week, the chapters are 6 and 7, but some selected sections, okay? And whatever we leave in the sections from chapters 4, 5 of the previous week, 6 and 7 of this week, we will cover them next week in a topic which is related to violation of OLS assumptions. So for this week, just follow the sections to be read. I have 2 videos here, which would be very helpful. I would suggest that you watch them after class. These are some repetitions, or most of them are repetitions of what I'm saying for you during our lecture or during our live lecture. So you would see like some repetitions here in case you missed something. It would be very helpful to go over all the videos that you see it posted on the weeks. And you have an OLS example here, which I will cover it or cover something similar to it today. We have videos. These 2 videos are videos from a previous class, like I guess like maybe a year or 2 ago, but they are very, very helpful. And once you start your practice questions, as you see here, practice questions are non-graded, but I usually offer it as an extra credit. So if I were you, I would just go ahead and do it. And each practice question is worth 3 points. So 3 points are counted towards your midterm if these practice questions are before the midterm date, and are going to count for your final exam if these practice questions are before the final exam date. Some of these practice questions, as we're going to do today, if we have the time, some of these practice questions are going to be done during our class time. Okay, from my experience, I see students, whenever you see non-graded students, don't go over it, despite the fact that these are very, very important for your midterm, for your final, for your assignments in general. So I suggest that you definitely need to go over it, even if it is not non-graded. If it is non-graded, it's still very important. Okay, and then this is just a reminder that you have a quiz on my lab. So whatever you see here about the quiz, one is just a reminder that you need to access my lab to take the quiz on Friday, the 18th of September. So remember, our quizzes are only 24 hours accessible. So you have to do it on Friday, the 18th. You choose your time. So the quiz, I guess it's an hour. I can't remember, is it an hour or 2 hours? I can't remember, but anyways, I will check it and send you an announcement. But anyways, it has to be done on Friday. Okay, so what we're gonna do today is, as you see from the title of week 3, is the multiple regressors, or more specifically, multi-regression analysis. So what we have done last week, let me just click on week 2. In week 2, what we have done is the simple version of a model where we have single regressor, where we have just one X affecting Y. Okay, so let's say in the example that we covered, which I posted for you right here, I posted here the in-class practice. Practice 1, which was a PDF file, and we had 2 questions. We covered just question 1, and today we're going to cover question 2. So in this question, in question 1 of practice 1, we had just a single regressor, where age, right? Was it age? Yes, age affecting earning. Okay, so we wanted to see the relationship between earning and age as the person gets older. I know that age increases as the person gets older, but I want to test it. So according to this example, a sample of 1,744 people were surveyed. They were asked how much they earn and what is their age. And all these data were collected based on the current population survey. And a model is estimated. And this estimated model was called the single regressor analysis, right? So it was just a very simple model, which is 1x affects y. In week 2, we're going, in week 3, we're going to expand the model, because I'm sure that there are multiple other factors affecting earning besides age. So we need to make sure that we are including these factors, because if we do not include these factors, then we're going to run into econometric problems. And these econometric problems are going to be discussed in details next week. Okay, so let's start today's lecture by reminding you of the main concepts covered last week. So again, anytime you have any question, just open your mic, okay? Open your mic and ask me as if we are in class, because with econometrics, you can't keep silent if you have a question, okay? And with Zoom, sometimes I don't see your message when you type on the chat box. So the best thing to do is you just open your mic anytime as if you're staying, as if we are in class when you raise your hand, right? So just open your mic and interrupt me and ask the question, okay? Because otherwise I'll assume that everything is perfect, you guys understand, I'll keep going. Okay, so let me see. Okay, so we are here. So again, last time we started with a single regressor model. And this model was very simple. I know that y depends on a certain intercept plus a certain slope multiplied times the variable x. And we said any econometric model has certain error term, which is we call u, or the error term. Okay, so we said that if I'm surveying this model over a group of people from person number 1 all the way to person number n, okay, so this is 1, 2, 3, 4, all the way up to n, then I have to have a sub I under each variable, right? So this is our regressand, or in math we call it the dependent variable, regressor, independent variable, right? And then we said this is our intercept. This one is our slope, which is equal to the change in yi due to the change in xi. Okay, so this is the slope. This is our main interest, by the way. So this is our main focus. Okay, so whatever we're doing on all this estimation analysis, our main concern or our main focus is on this coefficient, which measures the impact of x on y. And then we said this one, which is ui, is our error term. Okay, and then we said that when we estimate this model, we get an estimated version where we have hats. So ui hat, beta hat node plus beta hat 1 xi, and then we don't have an error term here. So we call this one as the population regression line, unknown. Okay, so we call this as the population regression line, and in our model it's just a single regressor type, and this is our estimated version, estimated population regression line. The difference, you can call this one as number 1, equation 1, equation 2. So if you subtract equation 1 from your equation 2, where equation 1 is the main data set, is the data set of the population, and if you subtract it from number 2, which is the estimated population based on the sample collected. So if you subtract 1 from 2, you get yi minus the estimated model is the estimated amount of errors. Of course, this is the actual data or actual model. This is the estimated model. And you can think of the errors as mistakes. And I hope to minimize my mistakes as much as possible to bring them to 0. This would be the best, right? Because I might have it negative errors if the estimation is bigger than the actual, or I might have it opposite, I might have it positive. So whatever the case, whether it's positive or negative, I want to bring it to 0. Okay, and then we mentioned last time that we do it as a sum from I equal 1 to n of the square, and we call it the sum of the squared errors. And this is called sum of the squared mistakes, or sum of the squared residuals, or the sum of the squared errors. Whatever the name, different textbooks, they call it different names, but the idea is the same. We want to minimize this equation based on, or with respect to, I should say, with respect to the coefficients I have, beta naught and beta 1. So I want to get these two coefficients that minimizes this distance. We also said that in a single regressor model, we get these coefficients as beta hat naught and beta hat 1, and this one is equal to the average of y, right, minus beta hat 1 average of x. So if you're giving me a set of people and this is their earning and this is their age, and I call this y and I call this x, and I have information here, right, in dollars, because this is how much they earn, and I have their age right here. So if I get the average here, I'm gonna call this earn bar, which is the average, age bar, right, which is gonna be like just one number. So if I get earning bar here minus beta 1 age bar here, I can get the estimation of the intercept of this relationship. We also said last time, and I have it posted for you as my handwritten notes on how to derive these two coefficients. And for the beta 1, it was like more of multiple steps until we were able to reach this conclusion that beta 1 is simply equal to the covariance between y and x over the variance of x. Or you can think of it, it's the covariance between age, earning and age divided by the variance of age. So if in just an introduction to statistics course, when you're given a data set in an Excel sheet, you can easily compute these two, because they depend on averages, covariances, and variances from a simple Excel sheet, okay? Again, as I told you, here, this is our main focus. Of course, every coefficient is important to us, but this one is very important, because this one would give me how, I'm sorry, the red is terrible, right? So let me just choose. Okay, so the change, it would give me the change in earning because of the change in age. And this is my concern. Of course, this would be like, what is the value of earning at 0 age? And I told you last time, at many times, the intercept has only a mathematical meaning. Okay, so let me use the example we had just to make sure that we are all on the same page. So the example that we had, actually I have it right here. So let me show it to you here from our last week class. We had earning. So we had earning, has a certain beta node intercept, has a positive relationship with this amount with the variable age. So I can say that beta hat 1, or I can call it beta hat age, it's just a notation, okay, is equal to the change in earning because of the change in age, and it's equal to 5.20. What does this 5.20 mean? So the 5.20 actually means that every time you start from the x, so it means for each additional unit increase in the x, the y would increase by this amount. In other words, for each 1 unit increase in age, what is the unit of age? Is years, right? So the person gets older by 1 year. So the unit here that I'm talking about is years, okay? So for each 1 unit increase in the person's age, or you can say it as the person gets older by 1 year, the earning, the earning, this is positive, okay? Just want to make sure that we can see that. So the earning increases by, increases by 5.20 cents. $5.20. And this is the model that we have. Also, the intercept is telling us that if age is equal to 0, our intercept is equal to, or earning is equal to $239 approximately. Okay. We also discussed other things last time. So we also said, once I get my betas, beta 1 and beta node and beta 1, this is not enough. I have to make sure that repeating this experiment multiple times, I'm going to get numbers which are very close to my estimated numbers. Like, my numbers are not coming by random chance, right? So it's based on a test, a statistical test, a hypothesis test, right? And I should be confident with high percent. Or in other words, I'm going to allow myself a confidence level of at least 90%, okay? So anytime you get a test, you have to have a null and an alternative. And we said my null is by default always, okay? By default, even in Stata and all statistical softwares, they set the default to be 0. So let's keep using our example. So my default is beta age is equal to the actual beta age of the population is equal to 0, okay? And this is like the long way of writing it. You can write it in a short way, which we're going to be using all the time during the semester. Is the shorter way, we're gonna say it like this: the expectation of beta age is equal to 0. And if I'm accepting this, then this one is telling me that age is insignificant, okay? Age is insignificant. So I have to perform the test, right? And of course I have the beta hat age is not equal to beta age, which is not equal to 0, okay? So you have to perform a test in order to be able to say, is it equal to 0, like has insignificant impact, or it has some statistical impact on age. So when we perform our test, we said we have multiple ways of performing tests. And in our, let me just have it like that so that you can read it in case you're writing after me. We said we have different ways of performing hypothesis test. And I told you that we have the t-statistic, right? We have the t-statistic, which is simply equal to the beta hat age minus beta age over the standard error of beta age or beta hat age. And by default, this one is equal to 0, right? So again, the t-statistic that you see here is the long way of writing it. From like most of the time, you will see me writing it this way: beta age under the standard error, because it's already subtracted from a 0, so I don't see it, okay? And that means when I go to my example, I need the impact of age, which is 5.20, over the standard error, which is given under, in brackets, under the coefficient, which is 0.57. So when you go here, all what you need is the 5.20, which is beta age, over the standard error, which is 0.57, okay? So you would write it like this. The t-statistic is equal to 5.20 over 0.57, okay? And this, did I compute it last time? Did I? I don't think so. Oh, wait. Let me see if I have the answer. Okay, yes. So it's equal to 9.12, okay, which is like a big number. So how can I make sense of this number? So if it is equal to 9.12, I need to compare it with a critical value. You have different options. You have the 1.96 under the 5%, right? And you have the 2.58 under the 10%, and you have the 1.64 under the, sorry. This is under the 10, and this is under the 1. This is the 1, okay? So you have these options. These are, the first ones are numbers, and these are percentages, 1%. So since the t-statistic is a number, I need to compare it with the numbers, right? And of course, the 9.12 exceeds the 1.6, the 1.96, and the 2.58. So you're done. All what you need to do is here, right? This is the rejection region. If I'm using the 5%, which is usually the default, 1.96, then the 9 is in the shaded region. What is your conclusion? Because the shaded region is called the rejection region, then I'm going to reject null. Rejecting the null, that the impact is 0. Rejecting the null, that the impact is insignificant. In other words, the impact is significant. Or you can say age has a significant impact or effect on earning. And this is based on the T statistic, okay? This is just one way. You can also perform the p-value, okay? So the p-value, I gave you the derivation of the p-value last time and you have it on your textbook. But again, our short way of writing it, or shortcut, is it's a two-sided test. So 2 times all the points that are less or equal to 9.12 in absolute value, just in case it's negative, okay? So you want to make sure that you're taking the absolute value. All right, so I don't have the number, but this is called the cumulative distribution table. And I took a picture here of the cumulative distribution table from your textbook, okay? And when you go to table 1, you will see that the Z starts from the negative 2.9, okay? So it starts from the negative 2.9. Let's say this is the negative 2.9, and it goes all the way to the positive 2.9. We don't have numbers below negative 2.9 or higher than 2.9 in this table. Why? Because as you see, the answer is going to be, the probability is 0, because as you move in these like tails of this distribution, the percent under the graph gets smaller and smaller and smaller. So the author decided not to have any number below negative 2.9 or higher than 2.9, which makes sense, okay? But in case you have a question in an exam that are outside the range of what you see it here, so you can actually use the online calculator, which, sorry, let me just refresh the page. So you can use the online calculator that you have it under week 2, which I posted for you under week 2. And let me show you how to use it. So you go, where is the practice? I posted here, and I said, click here, use the cumulative standard normal distribution function calculator. And you need to use that in case the numbers are outside the range of the table that you have in your textbook. Okay, so when you click here, you got this website, and the website is asking you for one thing. What is the Z-score? Okay, so the Z-score is simply the one that we have computed, which is 9.12. So you type 9.12, click go. See, it's basically telling us, sorry, my mistake. You know why? What is my mistake is I said it's negative the absolute, so I have to have a negative number, right? So let's clear this part, and let's also clear this part. Make sure that you clear it every time you're using this. And my Z is negative 9.12, right? So it's going to be negative 9.12. Okay, go. So as you can see, it's telling me the cumulative is 0%. And that's why we don't have it in the table. Any number below the 2.9 is going to get smaller and smaller and smaller, because the area under the graph gets smaller and smaller and smaller. So you actually don't need to compute to find it out. It's going to be 0. But in any case, as I said, you have it on your Sakai site under week 2 in case you want to compute it, okay? Or in case you have it in a question and you want to make sure that it's equal to 0. Any question? Any questions? Okay, so silence means acceptance. So I would say that you guys don't have any question. Okay. The other thing that we can do is, I said the p-value, and then we have computed it, and we found that this number based on the negative, see, it's negative and absolute. Okay, that's why I had to plug in negative 912. We said it's 0%, and this is saying that there is 0% probability that the null is true. Okay, you can repeat this. There is a 0% probability that the expectation of beta hat age is equal to 0. Then you can conclude that beta hat age is statistically significant. Okay, sorry, my handwriting is terrible, but the iPad is very slippery. So statistically significant. So whenever I say there is a 0 probability, then I'm basically rejecting the null, which is a good news, right? 0 probability means that reject null. And if I reject the null, I'm saying that I have a statistical significant impact of beta age or age on earning, okay? What else? We said also we can use, so this is number 2. In terms of testing, this was number 1, t-statistic, number 2, p-value, number 3, the confidence interval. The confidence interval is I take my coefficient, beta age, I add and subtract the standard error of beta age, and I multiply it times the critical value. I'm going to write it as CV, the critical value. What is the critical value? It's right here, right? These are critical values. 1.64, 1.96, 2.58. You choose whatever significance level you're going to perform your test on, and accordingly you choose your critical value. I'm sure that you understand the bigger the critical value, the wider is the interval, right? So if I multiply here by 1.64 one time, and then in another time, I'm multiplying times 2.58. Of course, with the 2.58, I'm going to get a wider interval. Okay, which one to choose? It all depends on if you are doing your assessment like an assignment or an exam. Choosing your significance level would depend on the question. If I have it specified in the question, or if I'm not specifying it, then it's up to you. In real life, it's up to you, okay, to choose what is the level of confidence you need to have in your test. Okay, so whatever I have done so far is just like an overview of what we have covered so far last week. And after we were done with a model, statistical hypothesis, I should say, hypothesis tests, the 3 types of hypothesis tests, we also talked about the measures of fit. So we talked about, okay, I'm done with the model. Okay, so we had this model, we're done with estimating the model, we got this estimated regression line. Now we want to see how good or bad is the model. And when I say how good or bad is the model, I need to have certain benchmark. My benchmark is in terms of explanation. To what extent age explains the variations in earnings? Okay, so if you're listening to today's lecture and all, oh my God, what is this? Okay, all my lectures, I would suggest that you take notes, because many things I mention, I can write them down. So I advise you to have like notes as if you're staying in class, right? Take notes as I'm talking. Okay, so you have estimated this model, which we call the estimated regression line. Okay, which is, let me go back just to connect all the information. So this is the estimated regression line, the one that has the Y hat, or in this example, we call it earning hat. Okay. We need to see what is the extent of explanation of age to earning. last time we talked about measures of fit, and we said that we have many measures of fit actually, but the ones that we are going to cover, okay, we covered the R square, which we said R square is the extent of explanation to the total explanation. Okay, so we said that this is the explanation of the model, and this is the total variation in the model. And if you open this up, we said that the explained sum square is equal to yi hat, my estimation. How far is it from the average, right? And then it's sum squared. So I need to have the sum. I need to have the squared. And I'm summing from I equal 1 to n over the total variation. Total variation is my model, actual model, minus the average. Again, total sum squared. So it need to have sum and the squared over I to n. So this is how it's written. Okay, and again, if you're taking just introduction to statistics, not econometrics, and you have all these, you can just, like you have, when you have an Excel sheet, you can just compute the average and get like the deviations. We said that another way of writing it is 1 minus the sum of the squared errors over the total sum squared. And we said the best ever R square would be 1, and the worst ever would be 0. So the R square ranges from 0 to 1. It has this range. If it is 1, then we're going to say age explains 100% of the variations in earning. If it is 0, then age explains 0 variations, which is very bad, right? It's the worst case. So when we go to our model here, we see this one as 0.05. You need to multiply it times 100% when you're explaining it, and you say, okay, age explains only 5% of the variations in earning. In other words, this model does not explain 95%, which is huge. Does not explain 90, which is the majority of the model, is not explained. So what we're doing today is we're trying to increase the explanation of the model. So we will try to increase this number by adding other factors to this model, by expanding this model and working with a multi-regression analysis in a hope that we can increase the explanation of the y of the model, or the dependent variable, or the regressor. Okay. So this was just one of them. We also discussed the standard error of the regression, and we said it's the square root of the sum of the squared errors over n minus 2. And then I said 2 here is coming for the correction of degrees of freedom, because if I open this one up, sum of the squared residuals, it's the sum of the squared residuals, errors, right? That's it. SSR is the same as the sum of the squared UI hat square. So why is it 2? If I open this one up, it's going to be the difference between my actual model minus my estimated model. And again, of course, it's squared because I have square here, and it's sum because I have the sum. If I open this one up, it's going to be beta hat naught plus beta hat 1 xi. So the 2 here stands for the coefficients that we are estimating. I'm estimating 2 coefficients, beta naught and beta 1. So I have to correct for degrees of freedom based on how many information I'm losing to compute this SER. The SER is more challenging than the R square because it doesn't have a benchmark, it doesn't have an interval. So every time I'm looking at let's say here, I'm looking at this number and I really don't know how to make sense out of this number, right? Because it doesn't have an interval from 0 to 1. or a critical value to compare with, or a significance level. So you just look at this number and you hope that this number is close to 0. Whenever you see this number is not close to 0, then it's not good, okay? It is more useful whenever I have two models that I'm comparing with. So let's say I have this 287 SER versus 280. Which one is better? Okay, the 280 is better, right? So it's usually SER used in terms of comparison between models. It's not as the SER like standalone comparison, like you don't have to compare it. And the other thing is, some people would take this number and compare it with the height of the regression. So the height, the intercept, is the standard error bigger than the height of the regression? Yes, that's not too much. Again, whatever you see here would be reflected here. If this is only 5% explanation, very bad model. This is 287 SER, still a bad model. Okay, so they do kind of complement each other. Okay, so we discussed 1 and 2. We also discussed 3, which is not root mean squared error, which is actually very, very similar to the SER, but I don't correct for degrees of freedom. So it's actually equal to SSR over N. That's it. So it's over the sample size. You don't have to correct for the degrees of freedom, and that's it. I want you to notice that if you have a large sample, then N-2 is not very different from N. So if I have a large sample, and by large sample, let's say I have 1,000. So if I'm dividing by 1,000, it's not going to be like huge difference if I divide by 998. So in large sample, it doesn't really matter which one I'm using, this one or this one, because they're going to give me very, very close results. Let's expand the model. And in expanding the model, when we say a multi-regression analysis, and the good news is, if you already understand what I have covered so far in last week and the introduction of today, then multi-regression analysis is not too challenging, okay? Because it's all about just expanding the model. So if I have yi is equal to beta naught plus beta 1 x1i plus beta 2 x2i, and then you keep expanding the model, adding betas and k and x's. So beta k x ki plus again the error term. So my model, instead of stopping here where I had just age, I'm going to say, okay, what about education? What about experience? What about the gender? Okay. So I have so many other factors that I need to take into my consideration to increase the explanation of the model. It's not only about age, right? It's about so many other factors that needs to be included in this model. So a multi-regression is just adding multiple x's to estimate the model. It gets challenging in the estimators, right? So if I want to get the estimated version of this model, just add the hats and remove the error term. So beta 1 x1i plus beta hat 2 x2i plus beta hat k x ki, right? And this is again the population regression line, estimated population regression line. And again, it's the same thing. The difference between these two is going to give me the amount of estimated error. So we go back to the same analysis that we have done last week and in today's introduction. Okay, and again, we do the same sum squared, minimization problem, and then I'm going to minimize or do a minimization problem of the sum of the squared residuals, which is this one, right? I'm just writing in a different way with respect to beta naught, beta 1, all the way up to beta k. So I want to minimize the sum of the squared mistakes of this model based on a set of coefficients, right? So it gets challenging in the computation of these coefficients because it's not just two coefficients. So if you go back here, when we had just two coefficients. Where is it? When we had, where? Did I might just had it? Okay, it's up here. Okay, so when we had just the two coefficients, this was the way of computing them. The intercept and one slope, and that's it, we're done, right? One is the average or the mean of y minus beta 1 mean of x, and the other one is the covariance between the dependent independent over the variance of the independent, and we're done. But now when it gets complicated with multi regressors, I'm sorry, when it gets complicated with multi-regressors, then we need to use metrics, okay? So the metrics that, of course, I'm not going to ask you to derive it using the metrics operations or anything, but I just want to show you how it looks like. So in a multi-regression analysis, I told you that you have y, I'm sorry, I hate using the red with the green background. I don't see it. Okay, so the y I, as again, we said it's equal to beta naught plus beta 1 x1 I plus, keep going, beta 2, beta 3, and so on, plus beta k x ki plus the error term. Okay, so you can write it actually in matrix form, and this matrix is going to be, okay, the first model for person number 1, the second model is for person number 2, and then keep going, and this is for person number n. Okay, so this is our first vector, okay, and it's equal to this huge matrix, and this huge matrix is going to have the first column is related to beta naught, the second column beta 1, the third is beta 2, the last is beta k, okay? And each and every coefficient is measured for each individual, okay? It's because I have n people. So it's gonna win, for the first one, which is the intercept, we always write it as ones, okay? So it's just a vector of ones, and I want to add like the dots here because it's just should be matching the y, okay? So like here, and then until the very last person. And for this one, which is x11, then I'm going to have x1 for person 1, okay? I have x2 for person 1. Keep going. I have xk for person 1. And it's a big matrix. Next, I have x1 for person 2. I have x2 for person 2. I have xk for person 2, and then go like that, and then I have again x1 for person n. I have x2 for person n, right? All these you should like fill it with other regressors, regressors, and then I have xk for person n. Okay, so as you can see, it's like a huge matrix. That's why we don't perform it by hand. It's easier to use data for that, but it's very important to show you how it looks like. And this whole thing is multiplied by the set of coefficients, beta naught, beta 1, beta 2, beta 3, all the way up to beta k. Right? So that if you remember your matrix multiplication, so it would be like this, the first row multiplied here, so this times this, this times this, this times this, right? The second one, and so on. You would get the equation, all right? And next, you will also need to add the error term, so plus I have this whole thing, error term, so I have error for person 1, error for person 2, error term for person or equation of person number n. Okay, and that's it. So we, in matrix formula, we write this as a capital Y. We write this whole matrix as the matrix of capital X, like the big X. We write this one as beta, and then this is the, usually write it as epsilon E, which is the error term. Okay, and based on that, so the beta hat, in order to solve this matrix, it's going to be, I'm going to give it to you, but you don't have to memorize it, or just you need to understand that how it works. So it's going to be x prime x inverse x prime y. I want you to remember how this is similar to the idea of beta equal to the covariance between x and y over the variance of x, like for the single regressor analysis. So this is like x times x, x squared, which is the variance down here, x times y for the covariance up here. So this way we can solve a multi-regression analysis set of coefficients. And when it comes to, and this is the last thing I'm going to mention about this matrix operation, is in terms of the sum of the squared residuals. I told you it's the sum of the squared u. Okay, based on our notation here, I'm just having it as epsilon. So the sum of the squared u, it's going to be e prime e, right? Sum of the squared errors. And I want you to imagine like it's equal to something like this. E prime, it's going to be like, let me use the u because I have it as u up here. So it's going to be like, okay, this is u1, this is u of person 2, it's transposed, right? So un, and then you have it here as u1, u2, all the way to un. Okay, so again, this times this, you get u1 squared. This times this, u2 squared. This times this, un squared, and of course the points in between. All right, so in multi-regression analysis, we do it, but it's based on a matrix operations. Again, you don't have, it gets like complicated. You don't have to, of course, memorize these matrix formulation, but you need to have it in your mind because this is how theta works. So in a multi-regression analysis, again, I'm sorry, I keep going to, let me go back here. In a multi-regression analysis, again, when you get the estimated model, let's say model number 2, okay, which is this one. This is our estimated model, yi hat. We get like multiple coefficients that we need to analyze. So let's take an example here. What is beta hat naught? Beta hat naught, again, is the intercept of the model at 0 beta, sorry, at 0 x1, right? At 0 x1, at 0 x2, at 0 x3, x4, xk. So when all these variables are equal to 0, this is the intercept of the model. And it's the same definition that we already had when we were talking about the single regressor analysis. Okay. What about, let's take, of course, the interpretation of this one is the same as this one, is the same as this one, but let's take one of them. So what about beta 1? Beta hat 1 is the change in yi hat because of the change in x1 I. But I have to add an important statement, which is holding all other x's constant, right? Because anytime I'm analyzing one factor, I have to hold this one constant, because I cannot mix all effects simultaneously at the same time. So whenever I'm analyzing one variable, I have to understand that I'm holding others constant. So we say holding all other x's. I'm writing it as x's so that to make your to make it easy for you to understand. But you can remove this x and say holding all other factors
I have
constant,
a question,
or you can
Professor.
say holding all other regressors constant. Okay, Othman, you had a question?
Yeah. Why are you holding all the
I can't
factors?
hear you.
Can you hear me now?
Yes.
Why are you holding all the other factors constant? Like, what's the reasoning for that?
Yeah. So as you can see it here, whenever you're setting this model, you're estimating this model, you try to break it out into the factors affecting it, right?
Okay.
So if I already have an effect here, which is attached to beta 1, then this one is a reflection of the effect of x1 purely, okay? It's not like absorbing the effect of x2. If I had this model like that, so let's see. Let me kind of rewrite this model like this. Okay, what about I have this model is equal to beta naught plus beta hat 1 x1i times x2i. In this case, beta 1 would be the effect of two factors together, right? The multiplication of two factors together. Here in the model that I have it as number 2, I don't have it that way. I have each one separately on its own in this model.
Yes, I can see that.
Yeah, so if it is multiplied, as we're gonna see, like the type of or a version of this model where we have multiplication like that, which we call it nonlinear model, we call it interaction type model. In these types of model, we cannot hold x2 constant when I'm talking about x1 because they are simultaneously affecting y through this coefficient. Okay.
Okay.
So the way the model is set up, as you can see it, each one on its own has its own coefficient. So that means each coefficient is just analyzing or is just absorbing the effect of the x attached to it, right? And with no regard to other x's in the model.
All right, I got you. Okay.
Okay. Of course, I want to mention something. When I'm like explaining it, you feel like, okay, yes, I understand it now. But actually, it's not the case because it might be the case that beta 1 is absorbing the effect of other variables in the model, right? Let's say, let me tell you something. What about if x1 is age, right? And x2 is education. Of course, as you get older, usually education gets more, right? So
It
there is a
should.
positive relationship. So it might be actually absorbing the effect of education in the age because a person who's like 15, the number of years of education is not the same as a person who's 18, if I'm assuming that I have a sample of people in a high school. Right? So it might be the case that beta 1 is actually absorbing the effect of age, but this is one of the assumptions in our week 2 is there is no connection between the regressors. We're making our life very easy, okay? We're going to break all these assumptions next week when we talk about something more realistic, which is, okay, no, age is connected with education. And actually, education might be also connected with gender. It might be the case that maybe females have more years of education than males, right? So it might be the case that each and every X is so connected that we cannot actually get a pure effect through these coefficients. So we're going to break these assumptions, even if it's not realistic now. So just take it as an assumption.
Okay.
Okay. All right.
Thanks.
No problem. So, okay, so beta 1 is, again, the way that we say it is I'm holding all other factors constant. Again, what about the rest? So the rest are just repetition of the same idea. So let me think about beta k, beta hat k. It's the effect on the estimated yi due to the change in xki, holding, again, just repeat, all other x's constant. I'm not going to write them again. Okay, you understand it now. So each and every variable is held constant. So let me go to our example. Where is our example? Okay, this one. Yes. So let's see question number 2. So in question number 2, it's the cost of attending college. Okay, and so this is the cost of attending college. So our dependent variable is the cost of attending college, how it's affected by the reputation of the college, the size of the college in terms of the number of students, whether it's a private or public, whether it's a liberal arts or not, whether it has a religious affiliation. And I'm just telling you these variables because I have seen this example before, but when you see an example or a question for the first time, you really need to read all the components, I mean, all the paragraphs right under that in terms of definition. Cost, tuition, fees, room, board in dollars, right? Reputation, it's an index used in the US, whatever, based on a survey, okay? It ranges from 1 to 5, where 1 is marginal, 5 is distinguished, good school. Size, measured in terms of the number of undergraduate students. D private, D liberal art, and D religion are binary variables. What is a binary variable? Binary variable is like this. It's, let's take one of them, D private. D private is a binary. It takes only 2 values, 1 and 0. 1 if this college is private, right? And 0 if not, or if public. So a dummy variable is just a variable that takes 2 values, 1 and 0. Okay, so this one is going to appear here. It's going to take 1 if the college is private. It's going to take 1 if the college is liberal art. It's going to take 1 if the college has a religious affiliation. If I don't see it in a regression, if this is 0, then this school does not have a religious affiliation. Let's say like Rutgers, we don't have a religious affiliation. So a regression for Rutgers, we won't see, let's say this one, okay, here. We won't see this one because it's a public, right? So but we do have like liberal arts schools inside Rutgers. So this one is going to take 1, 0, and 0. And it's case by case. So let's say if I have a group of, what is the sample size here? Can anyone see the sample size? Yes, it's right here. It's 100 national universities, right? So our sample size is 100. So this 100, so I'm going to have actually 100 equation. Okay, so let me relate that to my model here. So let me show you here. I'm going to have like 1, 2, 3, 4, Y100. So Y100 stands for the college or university number 100. Okay, so when you have a model like this is a multi-regression model, right? And again, as I told you last time, whenever you see a question about interpretation of the model, you have to move in order. So you move in order means that you analyze intercept, you analyze slope of the first variable, and sine, slope, sine, slope, sine, slope, and so on. And then you analyze the R square and the SER. Okay, so let's take an example. Of course, you have actually this you have this question posted under week 2 because we have done question 1 last week, and today we're going to go over this one. So you need to indicate whether or not the coefficients are statistically different from 0. As you can see, the question here doesn't tell you to use t-statistic, p-value, confidence interval, it's just open, okay? But I see that the easiest, okay, if I'm not asking you which one to use, the easiest one, okay, Part, you asked me a question, are you going to make available files from Stata videos? Yes, I'm going to make, you have it, actually, you have, the recording under the weeks, but anything that we talk about during our class, you will see it. You will see the videos uploaded and shared with you. Okay, so if I want to check whether a coefficient is statistically significant, let me focus on one coefficient, and then you can apply it to the rest. So let me focus on the size coefficient, okay? Or let me briefly just mention these. So at 0 reputation, at 0 size, at 0 D private, at 0 D liberal arts, at 0 D religion, the cost is equal to 7,311.17. Okay, dollars. Okay, next, reputation has a positive impact on the cost of attending college. And for each unit increase in reputation, and when I say unit, as you can see here, it's an index, right? It ranges from 1 to 5. For each unit increase in the reputation index, cost increases by 3,985.20 cents dollars. Okay. Size has a negative impact on the cost of attending college, which means the higher the size, the bigger the size, or the higher the number of undergraduate students, right, the lower is the cost of attending college. As the size increases by 1 unit, and when I say 1 unit, I have to go back to the definition in the question, and I say as size increases by 1 student, because this is the number of students, right? So as the size increases by 1 additional student, the cost decreases by 20 cents. A private college, for a private college, the cost increases by $8,406.79 on average. Okay. One thing that I forgot when I'm talking now is every time just add the word holding all other regressors constant. For a liberal arts college, the cost of attending college is below the sample average of about $416.38. If the college has a religious affiliation, the cost decreases by around $2,377. Again, holding all other factors constant. Okay, so whatever I have mentioned so far, I didn't say anything about statistical significance, right? It might be the case that all these, whatever I'm saying, is meaningless because the coefficient is insignificant. So I have to make sure that these coefficients are statistically meaningful, statistically important. So what I need to do is, let me clean this because I'm kind of a very messy when it gets to explaining. So let me just clean. What we need to do is we need to perform a statistical significance analysis using the T, P, or CI confidence interval. It's your choice, right? As long as the question doesn't ask you. So is it actually, let me just choose one of them, size. Is it actually true that size has a negative impact on cost? I see negative, but is it statistically important or not? So in order to answer this question, I need to perform a statistical significant test. And I'm going to use the T statistics. So I'm going to call it T of beta size, just a name. You can call it T, okay? So the T statistic is simply equal to the beta hat size minus beta size under the null over the standard error of beta hat size. And remember, in the back of your mind, remember, you have a null hypothesis that is saying that beta hat size is simply equal to beta size. I'm going to use the shortcut is equal to 0. So I'm hoping to get a low percent here. I hope to reject actually, because if I reject that, then this means that size has a statistical significant impact on cost, which makes sense. So what we have here is, okay, this one is 0. So you don't have to write it actually. So what you need to do is you take this number 0.20 over standard error, it's right here, 0.13. What you get is, I have the number, 1.538, okay? Is this statistically significant? Is it statistically important? You need to compare it with the critical values. And I told you before, we have 3 critical values that we are using throughout our tests. So as you can see, it's actually less than all of them. So it's less than the critical value under the, 1%, it's less than 2.58 under the 1. It's less than 1.96 under the 5%. It's less than 1.645 under the 10%. So it's less than all, we say it's less than all conventional levels. And the word conventional means all the 3 levels of statistical significance that we are using throughout the semester, and which is commonly used in the literature. So what does that mean? So if I have, let me just have a clean page. So if I have the cumulative standard normal distribution table, it has a critical values, and I'm using the 5%, just, it's usually my default, okay? So I'm using the 5% significance level. So I have here 2.5, it's a 2-sided test, 2.5%, 2.5%, right? The critical value here, my benchmark 196, my benchmark is negative 1.96. And the number I got is less, right? I got it 1.5, is it 1.5? Yes, 1.38. I'm going to approximate it 1.54. So what we have is the T statistic is less than the critical value, because the 1.54 is less than 1.96. Okay, so we are in the acceptance region, right? This is called the acceptance region. So if I'm in the acceptance region, I'm going to accept the null. And the null that says that the expectation of beta hat age is actually close to 0, which is bad news, right? So this means that beta age is statistically insignificant. Whatever I'm writing in this slide is very important, and that's why I had like a clean slide, because from my experience, students get so confused when it comes to the analysis of the test. So if I'm the acceptance region, I'm accepting the null. Okay, what is the null? The null is saying that this coefficient is very close to 0. And what does that mean? So if from here to here, students get confused. If I'm saying that I'm accepting the null, and this means that the coefficient is statistically insignificant, so you come to the final conclusion that, why I'm saying age and it's size, I'm sorry. Why I'm saying, you should guys stop me when you see me like a mistake here. I'm talking about size of college, right? So this is size, but you get the idea. Okay, so that means size has no statistical significant impact on cost of attending school. Does that have is this realistic? Of course, it's not realistic, right? Because we're sure that size has an important effect on cost. The question in the, on the practice is asking you what you're going to conclude. What if you find one of the coefficients, like I come back here, what if I come to a conclusion that size is statistically insignificant, has insignificant effect on cost? Do I just drop it from my model? The answer would be no. Like if I have a coefficient that I'm sure makes sense to me, that it's important to cost, let's say here, or the dependent variable in general, and it turns out to be statistically insignificant, should I just drop it? No, you can keep it, okay? And in a hope that you can enhance the model. Maybe whatever we are doing in week 1 and week 2 is not the best model to be used, right? Or it's not the best estimation, I should say. It's not the best estimation methodology for this model. So we can just keep it as long as it makes sense, and or it's coming from an econometric or an economic theory. Let's say demand and price. If the price statistically insignificantly affecting demand, it doesn't make sense to remove the price, because based on our micro theory, price is important. So just keep it and try to enhance the model, try to work with maybe different data, okay? Maybe different estimation methodology, because what we're doing so far is called ordinary least squares, OLS. This is like the introduction to econometrics. It might not be the best. It might be too simple for this model. It might be the case that I need a nonlinear model. It might be the case that I need log model, exponential model. It might be the case that I need interaction model. Like when I was answering Othman's question, I was like multiplying two variables together, which is called interaction model. Maybe I need an interaction model, right? But as long as the variable matching what makes sense to me in terms of what I understand from the real world, okay, what I see around me, or it's backed up by a theory, like microeconomic theory, macro, international trade, labor economics, something like that. Okay, so this answers, okay, so indicate whether, so number A, as you can see, number A indicate whether or not the coefficients are statistically different from zero. What I did for you only size, but you can repeat it for this, repeat here, 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 each one, even the intercept. Okay, so you're going to perform a t-test for each and every coefficient. And just one simple correction. I'm just telling you accept, but just you fail, remember it, fail to reject. Fail to reject. Okay, it's better than saying accept, because accept means that, okay, that's the best. It might not be the best. We're just based on our sample, we're failing to reject. Maybe I can change the sample and I can reject. Okay, so the best way of mentioning it is failing to reject rather than accept. It's easier in our head to remember it as accept, I know, but the accurate way of saying it is fail to reject. The second question, after you're done with all the coefficients, you need to compute the p-value of the null hypothesis of size. So let's do that. So I have already computed the teeth of beta size, which is equal to approximately 1.54. So let's do the p-value. You know already that the p-value is one step after you get the t-statistic, right? So let me do it here. So the p-value, it depends on whether you want to have a two-sided test or a one-sided test. Okay, so let me first do the two-sided test, and then I'm going to show you how we can do the one-sided test. Based on my null hypothesis, when I say equal or not equal, then I'm considering the left and the right under the graph. So it's a two-sided test. So the p-value, it's two sides times all the points which are less or equal to the negative absolute value of beta size. And the beta size, we found the beta size to be 1.54. So I need to find this number from the cumulative standard normal distribution table. And I told you this table that you have in your textbook goes from negative 2.9 all the way to positive 2.9. So you're confident that this number is going to be in your textbook. So let's go to the textbook and to the table. It's here. Okay, so I need negative 1.54. Where is it? Okay, so this is negative 1.5, and I need the 4, second decimal 4. Okay, so you go to all the way up to here, this number, 0.0618 or 6.18%, because you multiply it times 100. Remember, whatever you see here and there are numbers, which are numbers here, and whatever you see inside this whole table is the percentages under the graph. Okay, so the number that is matching our t is this number. So we go back and we write it down in the p. Okay, so we're gonna say, okay, it's 2 times all the points. Already we mentioned that. Let me just erase this. We already got the number from the table as 0.0618. You multiply it times 2 and you get it as 0.1236, which is, you can think of it as 12.36%. And then how can you compute, how can you make sense out of this number? Okay, let me just have a, so I compare this with the 5%. I'm using 5% significance level. So 12.36 is much bigger than the 5%. So you can think of it as there is a large probability that the null is correct. Okay, so there is a large probability that the null is true. So you come back to the same conclusions. Accept or fail to reject. Beta size statistically insignificant. Size has no statistical significant impact, right? So whatever you get under the T in terms of conclusion on the test is actually whatever you can get it under the P. Okay, so I have 12.36% probability that the null is true. In other words, that the beta size is equal to 0. What if, okay, so let me ask you this question. What if I want to perform a one-sided test? So whatever we were saying is a two-sided test. What if I want to start like that? My null is that the size, expectation of beta hat size, right, has a negative impact on cost of attending college. And the alternative, this is the alternative, it's going to be the opposite, right? So it's going to hold if the null does not. It's greater or it complements it, okay? So here, you're thinking that, wait, I'm going to just, yes. So here you're going to have a one-sided test, negative, and this is just the opposite part, okay? Can someone tell me what's going to be different in the t-statistic and what's going to be different in the p-value, and whether or not actually anything is going to differ? Anyone? So in terms of computing the t-statistic, is there any difference? Which is the beta size over, or the beta hat size over the standard error of beta hat size. So if I'm doing a one-sided test or a two-sided test, do you think the t-statistic is going to be different? Yes or no?
Yes.
Why do you think yes?
Because you're calculating it from two different parts of the I'm sorry, hold on, I'm just trying to walk over to sit down.
Mm-hmm.
You're calculating it from two different parts, so you're going to get two different answers.
For the t-statistic?
Yeah.
So wait, so now let's say the question here, I'm asking you to compute the t-statistic for the variable size. And I didn't mention whether you need to have it as a two-sided test or a one-sided test. I'm leaving it for you. Some students would say, okay, I'm not sure whether size has a positive or negative impact on cost, so I'm not going to say it's one-sided test. I better be more general, say equal or not equal, like here, equal to 0 or not equal to 0. And this way, I'm going to allow it to be positive or negative. I'm not sure, it's not equal to 0, okay? The other option that you have is if you have something in mind, let's say I'm 100% sure that age has a positive impact on earning. So definitely when it comes to a question like that, I would say, okay, I'm going to be using a one-sided test because age has a positive impact on earning, okay? Now,
but if it doesn't state that, then you kind of just leave it as like how you explained before, where it could be like equal to or
unequal.
Okay.
Yeah, usually we use it like actually in Stata, the default is equal or unequal.
Okay.
Okay, but now I'm just giving you an additional step, which is, okay, what if you want to be more specific about your test? What if the question is asking you, like, let's say I'm asking you, perform a one-sided test. Okay, so computing the t-statistic, when you see it here, like, look at the formula. Beta size minus beta over the standard error. Is there anything here that would be different when I talk about a one-sided test or a two-sided test? The beta size is the same, 0.20. The beta size is simply equal to 0 still, all right, under the null. The standard error is the same. So the t-statistic itself, there is no difference, actually. Do you agree?
Yeah, now that you explained it, I kind of understand it a little better. Yeah, I agree. I see.
Yeah, when you actually look at the components, like when I ask you, do you think it's going to differ between one side and two side? The best way to think about it is look at the equation. All what I need is the 0.20 and the 0.13. 0.20 divided by 0.13, it's the same whether I'm talking about one side or the two-sided test.
Mm-hmm.
So when I go back here, so having a one-sided or a two-sided test, this is going to be the same way of computation. What about the p-value? Do you think it's going to be different?
Hmm.
So here from the t-statistic, we got the number 1.54. We used it and we plugged it in here to get the p-value. We're multiplying times 2 because I have two sides, right?
Hmm.
Now I'm performing a different test and I'm doing one side. What do I need to do? How the p-value is going to be different for a one-sided test? It's easy. It's an easy question. Someone has to answer.
Well, because you're multiplying it by 2, it's going to be different.
Exactly. So now one side, what do you need to do? Just remove the 2, right?
Yes.
So it's a one side. I don't need this, right?
Mm-hmm.
I don't need this. And this is my answer.
Yes, because you're only doing it on 1 and not 2.
Exactly. You're doing just one.
Yes.
But there is something else that I need to take into my consideration is, okay, now I have my answer to this question is not multiplied times 2. So my answer is going to be 6.18%, right? And then I need to compare it with a significance level. So the significance level that you're comparing it with is
5%.
5%, exactly, right? So again, there is a high probability that the null is true, so it's compared with the 5%, okay? So the main difference between a one-sided and a two-sided test is the p-value, right? So the p-value, instead of multiplying it times 2 for the two-sided test, we're just taking it as is. We're taking it and comparing it with the significance level of 5%. Any question? No questions?
I'm good up to now.
Okay, great.
After you explained that part to me, I'm caught up now.
Yes, which part?
Like the t-statistic that we went over previously, before we got the p-value, like how we got 1.54.
Yeah, so it's
That's the part that I understand now. I was a
yeah.
little confused about it at first.
Okay, so you got it now?
Yeah, I got it now.
Okay, so it's kind of simple. Actually, every time, let's say, I want to get the t-statistic for reputation. Take this number, divide by this number. You get a t-statistic.
Okay.
Okay?
Mhm.
And but you need to compare it with the critical value, which is the 196, the 2.58, the 1.645. And if you don't understand how to get these critical values, let me know. Any question about that?
I'm good for that.
Okay, good. All right, guys. So let me give you 5 minutes break. Okay. I can continue, but I don't want to give you like so many information at the same time. So when we come back, we're going to continue from here. But in order to continue from here, I need to explain the F statistics. So when we come back, we will talk about the measures of fit for a multi-regression model. Again, R square, again, SER. So it's the same as we had it for a single regressor model, right? We had here sorry, we had here the R square and the SER. So we will talk about the measures of fit. We have exactly the same that we had it for a single regressor, R square, SER, root mean squared error, but we're going to add two more. One of them is the F statistic, okay? So now it's 2:01. I will be back at 2:06. All right. Hi everyone, I'm sorry, I'm 1 minute late. Okay, so let's continue. Okay, so we mentioned last week and in today's introduction about the measures of fit, right? And let me actually go here, and then I'll take an additional slide here. So anytime we're estimating a multi-regression model, we need to understand how well is our model, like whether it explains most of the variations in the dependent variable, or it's we need to enhance it. So again, as we did with our single regressor model that we talked about measures of fit, we're going to talk again about it. So we said that we have the R squared, right? And the R squared is about the explanation of the model. And it's not different from a multi-regression model or a single regression model. So we have exactly the same equation, which is the explanation of the model, the ESS over the total sum squared, which is equal to 1 minus SSR over TSS. So it's the same. And if you forgot how to derive it, you can go to our last week lecture. By the way, I'm still trying to recover last week lecture. I record all the lectures, but for some reason, last week lecture, we had a technical problem. So I'm following up with the help desk. Hopefully I can recover it. So I'll let you know about that. So the R square, whether I'm talking about a multi-regression or a single regressor, is the same. Okay, it's the same in terms of the formula. The second one that we mentioned, which is the standard error of the regression. Okay, standard error of the regression, right? We abbreviated SER, and we said it's equal to, so this was the abbreviation, so it's equal to the SSR, sum of the squared residuals, and I told you it was n minus 2 in the single regressor model, and we take the square root. And I told you why it's n minus 2. When I talk about it in terms of multi-regression, so remember here we're talking about the multi-regression, more than one x. It's going to be, instead of n minus 2, we're going to have more than one coefficient to be estimated. So it's going to be n minus k minus 1. And again, if you ask me why, so what is this SSR? SSR is the sum of the squared errors, right? I from 1 to n. That's it. So you can write it as the sum of ui squared, or you can write it as SSR. Okay, it's the same. And again, it's estimated. So when you open this up, it's the sum of yi minus yi hat squared. Okay, when you open this one in a multi-regression analysis, it's equal to beta hat node plus beta hat 1 x1 I, and then you keep growing all the x's, right? Like the example we had, like the size of the school, liberal arts or private or reputation and so on. So we have multi-regressors, okay? And then beta hat, the last one, k x k I. So when you try to count how many coefficients to be estimated, we have 1, 2, 3, 4, 5, 6, all the way up to k. So we have k coefficients to be estimated. And there is 1. Do you know what the 1 stands for? Anyone? Why we're subtracting 1? Dan, Parth, do you remember? from the foundation course. We mentioned about the subtracting the 1. Anybody? So you have the K stands for K betas, and then the 1 for the intercept. So the main difference between SER and a multi-regression analysis versus the single regressor, we had this one to be n-2 in a single regressor because I had only beta naught plus beta 1x. So this is 1 and 2. Now I have K, right? 1, 2, 3, 4, 5, 6, all the way up to K, and then I have the intercept. So it's K minus 1, K coefficients and the intercept. So, so we have the SER similar formula, but just we are adjusting the degrees of freedom. We have also the root mean squared error. So it's the root mean squared error. Okay, and the root mean squared error is actually like this one. It's the same, but we're not correcting for degrees of freedom. So again, it's like this, SSR over N. And if the sample size is large, then they are actually very, very close. Okay, so those three, we have already covered them in a different way last week for the single regressor analysis. Today, we're going to add to these. So we're going to add something called the adjusted R square. What is the adjusted R square? I told you last time that R square always increase when you add another regressor, right? The adjusted R square corrects for this problem by penalizing. It penalizes the addition of another regressor. So it's not every time you add a regressor, you will find adjusted R square increases. It sometimes increases, sometimes decreases. It's better to be used because it corrects for the problem we have with the R square. Because the R square, every time I add any regressor, it keeps on increasing. So I don't want the R square to be meaningful, right? Meaningless, I should say. So you want to use the adjusted R square so that it does not necessarily increase when you add an additional regressor. So when I say it's called adjusted, then you should see this in the formula, right? It adjusts, has some adjustment for degrees of freedom. So look at this, and we're going to adjust it. So we're going to add some adjustment. This is called an adjustment when you divide by n minus k minus 1. This is no adjustment because I'm not subtracting how many coefficients I'm estimating. So I want you to think about the adjusted R square as the adjustment over R square. So in order to do that, adjusted R square, we're going to repeat the same formula for R square, which is this one, right? But we're going to say, okay, it's 1 minus, I have to add some adjustment here. So I leave a space here and it's multiplied times SSR over again TSS. Okay, so what about the adjustment here? In order to adjust this one, I can divide it by n minus 1. And in order to adjust this, I can divide it by, I already said that, n minus k minus 1, right? Instead of writing them that way, I'm going to remove them from here. And I'm going to write them separately here. So it's n minus 1 over n minus k minus 1. And you can just remove this. So I'm just letting you know that these are supposed to be here, but we can rewrite it in a nicer way. And whatever you see here is the adjustment of degrees of freedom. Okay? So again, why the TSS is divided by n minus 1? So TSS, like here now, is just no adjustment. If I divide it by n minus 1, it's adjustment. Open this one up, it's yi minus y bar. I have to estimate the mean of y in order to get the TSS adjusted form. So that's why we're dividing by n minus 1. the second part, SSR, why I'm dividing SSR. Now, SSR by itself, it's not adjusted. If you want to adjust for degrees of freedom, you divide by n minus k minus 1. And again, why n minus k minus 1? I already mentioned it here. Remove k for the k coefficients to be estimated and 1 for the intercept. So the adjusted R square is simply the R square with some adjustment in degrees of freedom. The good news is it doesn't have to increase every time you add a new coefficient, right? So if I add adding an additional coefficient or variable, what happens to R square? So there are two effects. There is a positive effect and there is a negative effect. A positive and a negative. So if I add a new regressor, you know already that every time you add a new regressor, this SSR decreases. The amount of error, the amount that is allocated to other factors decreases, right? So, which is good news because you want actually the amount of error to decreases. So the positive or the good news is that a decrease or a reduction in SSR. The bad news is is this k, because I would keep counting additional coefficients, this k would increase. So the k increases. And it's bad because when k increases, this means that the adjusted, I'm going to write it as ADJ, R squared decreases. And this one implies that the adjusted R squared increases. So as you can see, if it increases is a positive effect, good news, right? It decreases is bad news or a negative effect. So as you can see, every time you're adding a new coefficient, it doesn't have to be the case that the R square, the adjusted R square increases. When you go here to the R square based on its formula, every time you add a new regressor, the SSR decreases and R square increases mathematically, right? Because this decreases, it has a negative sign, the R square increases. So that's why every time you add a new regressor, the R square increases. Doesn't have to be the case for the adjusted R square because the adjusted R square has two effects, a positive effect that makes it increase and a negative effect that makes it decrease. And then the both are going to, or the final effect is going to be determined on which force is stronger. Okay, so one thing I want to mention is if I have, again, a large sample size. If I have a large sample size, let's say I have a sample of 7,000, I have a sample of 1,000, any big number. In our textbook, a big sample size implies 30 observations or more, okay? And all the time we're working with more than 30, definitely. So if I have a large sample size, then really the correction does not make a big difference. Sorry, the correction does not make a big difference, right? Because this part, if I have a large sample, it's not like going to be like a huge difference between R squared and the adjusted R squared. So you won't see it, okay? Few things to note is about the R square or the adjusted R square. Is, and it's important, is if I have high R square or adjusted R square. So it means that the regressor or regressors explain, like it reflects how explain the variation in Y, okay? But remember, you can still, or our model can still so our model can still have some econometric issues, right? So our model can still have omitted variables, like I might be forgetting an important variable that I forgot, like an important variable that I forgot to add to the model. I might have insignificant coefficient. So a high R square or a high adjusted R square does not mean that the coefficients are statistically significant, right? You can still have insignificant coefficients. You can still have biased coefficient. What do you mean by biased coefficients? I'm going to talk about that. So biased coefficients means that, let me go back here to our, what is the biased coefficient? Suppose that this number, as you can see it, let me talk about this one. Suppose that this number is, you see it as 41638. Suppose that the actual number is 420. Okay, so this number is approximately 416, and this is the beta hat, D liberal arts. Okay, suppose that the B actual is 420. So this means that there is a gap between these two. Okay, and this gap is about 4 points. So in this situation, I would say, okay, beta hat is biased because it's not equal to the truth. It's away from the truth. It might be 416 the best, right? I cannot get the 420 out of my sample of the 100 national universities. I might need to expand my sample to maybe 500 or 300 or 200, double it at least. And maybe I would be able to get closer to the truth, closer to the 420, okay? So a biased coefficient is the distance between my estimated coefficient and the number actually computed in the population, or the number actually known in the population. And this is under the assumption that it's known. Okay, so an example would be like, let's say you want to know how much you would earn after you graduate from an economics department with a major in economics, let's say. So you Google search and you find that students you graduated from an economics department with an economics degree would get, for example, around 45,000 on their first job. Okay, this is just an example. So this would be your population number. You would go ahead and you collect data from a survey on students graduated with economics degree, and you ask them. And after you ask them, you want actually to compare, okay, this is the 45K that I got from Google. I would consider this the actual or the true data. And I'm going to compare it with the survey data. And the students told me that they got 42K for a sample of 100 students. So this coefficient is biased, right? Because it's away from the truth by 3 points or 3K. Okay, so the results that you get for the R square does not mean that you have unbiased does not mean that you have a biased coefficient, right? It doesn't give you this information. It would just tell you all about one word, explanation of the model. Okay, it also doesn't tell you whether you have other econometric problems, and these other econometric problems, we will cover them in details in the coming weeks. Okay, so all, like, the main job of R square is about the explanation of the model. It's just going to tell you, it explains the model with this amount, 90%, 50%, 5%, as we have it on our example, and that's it. Let's go to another measure, which is, I consider it very important, and which you have it on your practice question number 2. Which is, okay, let me just take here, which is F statistic. What is the F statistic? So what if I want to perform a test for more than one coefficient? So I want you to think of the F statistic as similar to the idea of a T statistic, but on more than one coefficient. So you know that the T statistic had a null hypothesis like this: whether the expectation of beta hat, let's say 1, is equal to 0, right? And the alternative was whether the expectation and this is a two-sided test, beta hat 1 or beta hat 2, whatever, is not equal to 0. So this is a two-sided test, and we used it to perform our t-statistic, p-value, and so on. What if I want to test two coefficients simultaneously, their impact together? Okay, so it's not only about size, but I also want to check size with whether the college is a liberal arts or not together, okay? Or whether I want to check size of college with religious affiliation together. So in this situation, I'm going to adjust the test and call it F test. So this one would be like adding other coefficients. Expectation of beta hat 2, and you can actually expand it as much as you like, right? Expectation, it's a multi-regressor model, so you can go all the way up to a big model where you have k regressors. And the idea is still the same, whether they equal each other and they are all equal to 0. And whether this one is not equal to beta hat 2, right? And let me just wait. I'm just gonna make it easier. Okay. So it's not equal to 0, and or expectation of beta hat 2 is not equal to 0, and or keep going, right? And or expectation of beta hat k is not equal to 0. So this is called the null hypothesis of the F test. You're testing multi coefficients at the same time. So in order to do that, we have different F statistics. So let me choose one that is based on what you have learned so far, because we keep adjusting it depending on okay. So if I'm doing the F statistic on all the model, right? All the x's in the model, all the coefficients in the model, or let me just be more specific, all the betas of the model. Or selected betas. So if I'm doing it on all the betas in the model, like the null hypothesis that you can see now, then the F statistic is simply equal to the explained sum squared over how many regressors I have over k, so it's adjusted, divided by the SSR over n minus k minus 1. Okay, I don't know why it's written like that, so it's n minus k minus 1. N minus k minus 1. Okay, so this is if I'm performing it on the whole model. Okay, and you can actually write it in a nicer way. So I want you to think about this is explained sum square. Just remember it, it's the sum of the distance between yi hat minus y bar squared. Okay, and what about this one? It's the sum of the error term hat square, which is equal to the sum of yi minus yi hat squared from I equal 1 to n. Right? So, and again, I'm not going to adjust why is it k, why is it right, so you already understand it by now. You can actually write it as it's when you divide a total over a sample size, it's the mean. So we can call it the mean squared explained, mean squared explained, because it's explained. So it's just the mean of the explanation of the model divided by the mean squared residuals. Mean squared residuals or errors. Okay, so this is the F statistic for the whole model. And when you do estimate a model on theta, this is like it's going to be given to you. You don't have to estimate. You don't have to do anything. It's going to be like in the output of the model, as I'm going to show you later. Okay. What about if I want to do it on selected betas? Okay. So if I want to do it on selected betas, then I'm going to go back here and I'm going to adjust. What if I just want to do it on the first two betas? I don't want to do it on the whole thing, right? As I said, the whole model is already by default computed in the output of theta. So this one would be like this. Okay, so if I want to do it on selected betas, let's say, for example, beta 1 and beta 2, and I really don't care about the rest. Remember, your model is big, right? Yi is equal to beta naught plus beta 1 x1, right? And then you keep going, plus beta k x k I here and I here. This is already an I here. Okay, so this is your model. So what if you really don't care about all the keys, you just want to have it for beta 1 and beta 2, that's it. So if I want to do it on selected regressors, then we're going to compute something called restricted and unrestricted. What is a restricted model? A restricted model is the model where I set all the rest zeros. I don't want to see it. Okay. Restricted model is I'm restricting all the coefficients that I do not need to be equal to 0. Unrestricted is the model that everything is there, right? Which is the original model. So we get a new formula for the F stat for a subset of coefficients, some selected regressors, right? Or some selected coefficients. So the F statistic would be F is equal to the R square unrestricted minus, I'm going to write it as R-E-S-T, but it's unrestricted. The model as is, the R square of the model I have originally. And the R square restricted, where I'm restricting the coefficients I don't need to be 0. So I'm minimizing the model. I'm going to give you an example, right? Divided by 1 minus R square unrestricted. And in the F statistic, we are always adjusting for degrees of freedom. So here I have Q. Q here stands for the coefficients restricted. So number of restrictions. So how many coefficients I'm restricting? Let's say here I have 1 and 2. So Q is equal to 2. So I'm restricting coefficients to be equal to 0. And then here, N minus K minus 1. And this F statistic has a distribution from the F table, then the F distribution table that has Q, number of restrictions, degrees of freedom, N minus K minus 1 for the denominator. Numerator, degrees of freedom, denominator, degrees of freedom. So if I'm only testing the statistical significance of 3 coefficients together simultaneously, then Q is equal to 3. And this part is going to be your sample size, how many coefficients you have in your model, minus 1 for the intercept. One thing to mention is N minus K minus 1 in a large sample is approximated as being infinity. So when you go to the table of the F table and try to get the critical value, you actually look at the row where it says infinity, because if the sample is large, we usually approximate it to infinity. So I'm going to, I'm sure that this kind of sounds complicated, but let me give you an example. So suppose that we have a demand. I'm going to take the idea of a demand for college and give you a similar, okay, so let me show you this, an example. So the demand for college is equal to 370 intercept minus 1.1, the cost of college in dollars. It has a standard error. Remember, everything that is in brackets right under the coefficient is the standard error of the coefficient. Minus 1.5 distance, how far you live away from college, has a negative impact on your demand for college, assuming that you don't live on campus, 0.5. Plus 0.97, the rank of the school has a positive impact on your demand, of course, and this is 0.37. And assume this model has an R square of 0.468, so 46.8% of the variations in the demand for college is explained by cost, distance, and rank. Okay, so this one is telling us 46.8% of the variations in the demand for college is explained by 1, 2, 3. Okay, so you see the R square now, and you look back here, we said I need an R square restricted and R square unrestricted. The unrestricted is the original R square of the main model. So I didn't do anything, right? I didn't restrict any coefficient to be equal to 0. So we call this one unrestricted. Okay, next, suppose that you want to perform a test, a joint test, in which you want to test the simultaneous impact of cost and rank on the demand for college, and we say they are equal to 0. Just notice that I have a different way of writing. The null hypothesis doesn't matter. You can write it as had, expectation, right? It doesn't matter. So let me write it the way I explained it so that you don't get confused, but just you can write it as I'm writing it now. So the null hypothesis, it's the expectation of beta cost is equal to the expectation of beta rank is equal to 0. And the alternative is that this one is not equal to 0 and or okay. What is a restricted model? This is called the unrestricted. The original model is unrestricted, and the R square that comes out of it is the unrestricted R. Now, based on this test, hypothesis test, I'm going to restrict the model. I'm going to set this one is equal to 0 and this one is equal to 0. In other words, I'm not going to have them in my regression. So if you do that and you re-estimate the model, the demand for college is equal to 405 minus 1.68 distance. As you can see, we don't see the cost and rank because they are restricted. And the R square that comes out of this model after you re-estimate the model is 0.442. And this is called restricted model and restricted R square. Now, compute the F. Just follow this formula. Unrestricted, restricted, 1 minus unrestricted, right? So we're going to just plug in what we have. So it's going to be equal to 0.468 minus 0.442 under Q. How many restrictions we have? Under the null, I have 1, 2, divide by 2, over 1 minus 0.468 over n. I have a sample size. I didn't tell you that. So the sample size is 500. So we have a sample size of 500 minus how many regressors? K, 1, 2, 3. 3 minus 1 for the intercept. So this is the correction for degrees of freedom. You will get it as 0.013 over 0.00107. And this is 12.1. So this is the F statistic from the test. Again, it's like the T statistic. You get the number, you need to compare it with the benchmark, which is the critical value. So you need to set your significance level before you move to the table, right? So the F statistic is also, it's made out of squares. So you don't have a negative sign. I mean, like you don't have a negative side in the distribution table. It looks like this, right? And the shaded region is the, again, rejection region. And this is the acceptance region. And this is the critical value. And the shaded region is the area under the graph. Okay, I need to find the critical value in order to compare the 12.1. I'm like, is the 12.1 in the shaded or in the unshaded region, so that I can say something about my test. So before you decide what is your critical, I mean, like before you try to look for your critical value, you need to decide, am I using 1%, 5%, or 10% significance level? So you have to decide on that before you go to the table. If you are in an assignment or an exam, sometimes I would tell you, use this. In real life, it's up to you. So let's use the default, because actually in your table, and I mean in your textbook, you have 3 pages and each page is for a different significance level. So if I'm using the 5%, I have the table here for you. So for the 5%, you go to table 5B, okay? Table 5B, page 727, okay? Now, I have to decide what is the degrees of freedom for the numerator and denominator, okay? Now I know that for my numerator, I have Q restrictions, okay? So let me show you back here so that you're not confused. Numerator degrees of freedom, 2. Denominator degrees of freedom, 500 minus 3 minus 1 is 496. So I'm going to this table looking for a numerator of 2, denominator of 496. So you go here, up here, 2. I need this column right here. I need this column, 2, for the numerator. Now, denominator, can you find 496 in this table? Of course not, because this table ends at 120. And that's why I told you we're going to be using the infinity sign. Infinity, that stands for a sample that is larger than 120, we can approximate. So that means our critical value is 3. And I want to let you know that most of the applications, I would say like 99% of the applications that we do in during our semester, it's going to be using infinity row, right? Which means I have a sample that is bigger than 120. So you always go to the very last row because we are approximating. So under the 5%, if I decided to use the 5%, then I'm going to go to the table of the 5%, right? And then after I go to the table of the 5% significance level, I go to how many restrictions I have 2, I found my critical value. Okay, so this critical value based on this table is equal to 3. Again, I'm going to change the color. So it's equal to 3. What about this number? This number is bigger than 3, so let's say it's here. So I'm going to say 12.1 is greater than the critical value of 3. Okay, so we are in the rejection region. Reject, null. Okay, and if I'm rejecting the null, I'm accepting the alternative, right? So you accept the alternative. And what the alternative is saying, this is the alternative, that beta hat cost and beta hat rank, right? One of them is not equal to 0. One of them has a statistical significant impact. So accept the alternative that you see it here. I'm not going to rewrite it. You have it here. And the main conclusion is cost and rank are jointly, and this is important, jointly statistically significant. Okay, so they are jointly statistically have a joint statistical significant impact on the demand for college, because I'm kind of combining their effect together using the joint test, which is the F test, and based on our critical value and the number that we got, we found that we're rejecting the null and they are jointly statistically significant in the model. Okay, let's go back to our question. We have something similar here. You want to test, so number C, you want to test simultaneously the effect of beta size and beta liberal arts. So you have two things that you want to test simultaneously, right? So just cleaning my mess. So in order to do that, we're doing, again, an F test. And then the F test is done jointly on these two coefficients. How many restrictions we have? Can someone tell me how many restrictions? How many restrictions? How many coefficients to be tested? What is the Q? How many restrictions? Lewis?
I'm sorry, what was the question?
So I'm saying how many coefficients to be tested under the null?
2.
Exactly. So again, Q is equal to 2, right? And the question is giving you an F test of 1.3. So it's already computed for you in the question. Do you think that beta size and beta liberal arts are statistically significant? Can someone answer the question number C? How about Parth? Where are you, Parth?
Yeah, just a second.
Okay.
You want C or?
Yes, so in C.
Regarding the null hypothesis?
Yes, so we got in a hypothesis that beta size and beta liberal arts are equal to 0. The question is giving you already the F statistic. You don't have to compute it, right? They computed for us already, you know, the F statistic that we just computed, like similar one, like this, they have computed for us. So the question is already giving you the F statistic. Like we computed it, remember, in our example, 12.1. Now we need to answer this question. Can you reject the null hypothesis? What do you think?
I don't think so.
What is the critical value?
5%?
What is the critical value that you base your answer on? Do you understand the question? Hello. So here I have, this is F, and I have two restrictions. This is the numerator, and this is the denominator, infinity, degrees of freedom. So we go to the table again, F to infinity, it's gonna be like 3.00. So what we need to do is 1.23 is smaller than 3.00. Okay, so when I have the F statistic, it's like, again, one-sided. It's all made of squares, so it's only positive, right? And this number right here is 3, which is my critical value. The 1.23 is here, right? 1.23. So do you think you reject or accept or fail to reject? What is your answer to this question? How about Dan? Or Part, if you have an answer, let me know.
I fail to reject because it's not in the under 3.
Exactly, yes. So if this is like here, fail to reject because you're not in the rejection region. And then what is your, like, it's not asked directly in this question. So if you fail to reject, what does that mean about the size and liberal arts effect?
I'm sorry, miss. You said it failed to reject because it wasn't in the region. Is that what you said?
Yes, so here this is called a rejection region, right? Rejection region, and this is fail to reject, or we think of it as accept, okay? So your critical value is 3. Do you know how we got 3?
Yeah.
From the table that I showed you, like in the other example, it's the same. So we found 3, and then this question is already giving us the 1.23. We don't have to compute it. So we are comparing the 1.23 versus the 3. Since it is less than 3, right? This one is smaller than 3, then you are in the acceptance region, accept or fail to reject.
Okay.
In other words, I'm failing to reject what? Can someone tell me, like, what is your null hypothesis? You're failing to reject what? What is your null hypothesis based on this question? Just read number C. It's written in front of you, number C.
B size equals 0. And
Yeah, so you reject, exactly. So you think of it as you fail to reject, or you're accepting this. You're accepting that the impact of size and whether the college is liberal arts simultaneously insignificant, right? Simultaneously, their impact is 0. You get that?
Yeah, I gotcha.
Okay. Any question? The main difference between this example, I mean, like this question, and the one that I just did now, is this one is much easier because it's giving for us the F statistic already computed. The one that I did, I have 2 models. One we got from which the R² restricted and the R² unrestricted, and we used them to compute the F. Okay, but usually most of the time I would just give you the F and ask you to interpret the result. Okay, so when you come to a conclusion where 2 variables are statistically insignificant, so you might think that, okay, what about I re-estimate the model, okay, and remove them from the regression, like if they are both simultaneously insignificant. So how about if we can, as you can see in number D, how about if we can eliminate the size and D, which is the dummy for liberal arts, from the regression. So when you remove them, you got a new regressor, I mean a new regression. Then you start thinking about, okay, which one is better? Is it this one or this one? I can see that the I can see that the R² is almost the same. There is no huge difference. I see that this one is smaller than this one. So it might be the case that this model is slightly better. I still need to enhance it, but it's slightly better. Okay. Okay, so let's continue. So the F statistic is used for joint statistical significance. I showed you how to get the number from the table, and I told you that all the time we're working with with a sample size that is, and this is very important because most of students get confused. All the time we're looking at the very last row, which is the infinity, because our sample size is bigger than the numbers here. If it is smaller, like if it is 120, if it is 90, then you know what to do, right? You get 30 versus 1. This is your critical value, and so on. Okay, this is about the measures of fit. So the measures of fit are used in order to test the statistical significance of the model: R-square, adjusted R-square, SER, root mean squared error, and the p-value. Okay, so let me see what I want to do. We have two things that we can do. I can show you Stata. So let me show you Stata, and then I'll continue with other things. So I'm going to share with you my computer. As I mentioned at the beginning of today's class, that you have the practice questions of Stata. If I have time during our class, I would stop and ask you to do it, so that I'm sure that you don't have any question. It's non-graded, as I said at the beginning of the class. And then I'll be like here. If you have any question while working, then you can, we can do it, but I'm not sure whether we have time to do it today. So we will see. Okay, so I'll be sharing with you my screen. Okay, so I have different options here, so let me work with this one. Okay. By now you should have watched the videos of week 1 and week 2. Okay, today is week 3. And if you watch the videos, then you can understand how to create a path, right? How to create a file to capture all your results, how to load the data set. Okay, so anytime you're creating a do file, because you can always do the interactive, like use the interactive way here by typing all your commands right here, but this is not the way I want you to learn Stata. I want you to create a file, which we call it the do file, in order to have all your commands, and then you just click on this command right here to execute it and get the results. So let me see. Okay, so let me use this one. I have different options, but let me use this one. So I'm going to, okay, I don't have anything open, so I'm not going to close anything. And then I'm going to load the data set. Of course, it's much better to click execute, and then it's going to execute the whole file all at once. But since you are still learning, so I'm going to highlight step by step. So we have here loaded the data set. Okay, you can, based on the videos of week 1, you can summarize the data set, right? Summarize it by looking at how many variables I have, how many observations. I have 420 observations, how many, for all of them, they are all 420, total enrollment, okay, the mean, standard deviation, minimum and maximum. Some of the questions you see in practice 1 would be like, summarize the data set, and I would ask you questions about, okay, test score, what is the mean? I would ask a question, student-teacher ratio, what is the standard deviation? Average income, what is the maximum? You know, so you have all the information right in front of you for practice 1. I would just like to ensure that you can read it, okay? So if you haven't done practice 1, I encourage you to do it as soon as possible. It's a straightforward, it's an easy one, but just make sure that you're not missing anything. The correlation command, again, is covered in week 1. And if I want to create a correlation between two variables, and if you're looking at these abbreviations and you're not sure what does that stands for, with each do file you have on Sakai, you have a Word document which is called data description. On the data description, you have the abbreviations and what does that mean and how it's measured. Is it in dollars, in cents, in miles, whatever. It's very, very important to read the description of the data before you start. And this one is just showing us a correlation between the total enrollment in a school versus the number of computers per student. And as you can tell, the number of computers per student is negatively correlated by the total enrollment. Like the higher the enrollment in a school, the lower is the number of computers per student, and it makes sense, right? So you can't like have every student in class when the size increases. Size of students increases, like it's not easy to have a computer per student. It's kind of costly. So what you have in green here, anytime you're typing like a star at the beginning of any sentence, then it's not going to be executed by Stata. These are like some answers to or some observations about correlations and the number of observations, the minimum, the maximum, and so on. If let's say you're working in an assignment and you want to ask me a question or you want to write me a note, you can always like type a star and then type whatever message you want to tell me, okay, in case you have a question, let's say. All I mean is that anytime you have a star, it means that it's not going to be executed by Stata. Okay, now let's start the OLS. As you can see, this is a multi-regression analysis. So test score as a function of, so this is your Y, as a function of student-teacher ratio, the percentage of students learning English, number of computers per student, okay, and enrollment or total enrollment, all right? This is a multi-regression model. If I stop here, like if I stop here, let's say here, this is just a model with 1x, okay? And as you can see, this is a single regressor model. This is what we had last week. And I told you last week that this is the beta. So this one is telling me that for each additional student, this is student-teacher ratio, for each additional student per teacher, the test score drops because it's negative by 2.20, let's say 2.28 approximately points. It's very important to know what's the unit of measurement, right? For the dependent variable so that you can use it in the interpretation of the model. If I'm asking you whether student-teacher ratio has a statistical significant impact on test score, can someone tell me, like based on the T or the P or the confidence interval? We have 3 ways are reported here. What about the T statistic? Is it statistically significant? So let's ask Dan, what do you think? Hello, is Dan here? Okay, how about Othman?
I'm still trying to solve it.
You don't need to solve anything. You just look at the T statistic. Based on whatever number you see, which is the negative 4.75, do you think it's statistically significant? Like based on, let's say, based on the 5%?
Yes.
Why?
Because it's less than the 5%.
No, wait, the T statistic is not percentages. The T statistic is a number. So anytime you're comparing the T statistic, you need to compare it with the number, which is called the critical value. Okay, so what is the critical value under the 5%? Do you know what's the critical value under the 5%?
No, I don't.
So which is the 196, remember? It's the 1.96
Oh, from the early, yes.
from what I explained before and from the
Yes,
table.
yes.
So this number in absolute terms is greater, or even without absolute terms, it's less than negative 1.96.
Yes.
So it's in the rejection, it's in the tails of the distribution, whether from the left or the right, it's in the tails, right?
Okay.
So it's in the rejection region. So you're rejecting the null, right? Do you understand up to here?
Yes.
So when you reject the null, what the null is saying that the expectation of the coefficient of student-teacher ratio is equal to 0. However, we're rejecting that. In other words, if I'm rejecting, which is good news, then this coefficient is statistically significant.
Okay.
Do you get that?
But why though? Like, can I like?
Yes. So, all right. So let me go back to sharing my
But
iPad.
why is it also a good thing that you are rejecting the null instead of?
Because it depends on what is your null hypothesis, right? So let me show
So in
you.
this case specifically, it's a good thing.
Actually, it's not only this case, because the default is, like the default in Stata, every time is that this coefficient is equal to 0. It's meaningless, okay? So let's see. So the coefficient, so let's see, let me just use. So student-teacher ratio was equal to, based on the results I have on Stata, 698.93 minus 2.279 STR. Okay, let me use its second decimal approximation just to be 8. Okay, STR. What is your null? Your null hypothesis is like what the expectation of beta hat STR is equal to 0. The alternative is that the expectation of beta hat STR is not equal to 0.
Okay.
So if you accept this one, means that it doesn't have an effect. It's insignificant. So this one is insignificant. This one means that significant effect, because it's different from 0. It could be positive, it could be negative.
Okay.
Right? And this, like, when you ask me, is it for this specific case? I'm saying that because we know that student-teacher ratio should have a significant effect, right? Then I hope to reject this.
Okay.
So how can I reject or accept? So this is the cumulative standard distribution graph. I have critical values here, 1.96, negative 1.96. And I want you to make sure that you understand how we got this. Okay? Because this is from the table. The number that we have on in the output of Stata, it's telling us that T statistic of beta hat STR is equal to negative 4.75. So it's somewhere here in the rejection. So the tails of the distribution are the rejection region.
Okay.
So based on that, you are
both tails, like front and back.
Exactly.
Okay.
So you can actually take the absolute value and say, okay, 4.75 is here, or the negative is here, so it doesn't matter.
Okay.
So you're basically in the rejection region, so you reject null. And this is good news for you, because you're actually, you were like 100% sure that student-teacher ratio affect the test score. The number of students in class, the higher the number of students in class, the lower is the test score, like the less is the attention of the teacher per student, and you would expect a lower test score on average. So you're rejecting the null, and you're saying that beta hat STR is significant. Do you get that?
Yeah, I understand it.
Okay.
All right.
So any question before I move back to the Stata? Any question?
Up until now, nah, I'm good. Just got to write this down. If you just give me 1 sec.
Sure. And I want you guys to understand for next time, because like I felt like some of you don't understand how to get the critical value. So I want you to read from chapter, I think it's chapter 2. No, sorry, it's chapter 3 of your textbook, how to find critical values from table 1. Because we need critical values in order to be able to use it as a benchmark for our test. Okay. All right. So you're done?
Yeah, I wrote it.
Okay. And anyways, I hope that towards the end of this class, today's class, it's recorded, because last time I had issues. So I hope that you will be able to get the
It says it's recording right now, so I think it should be.
Yeah, the thing is, last time it was also saying recording, but I did a mistake where I saved it on my computer instead of the cloud. And then after I was done, it said that you don't have a space on your computer. So it couldn't
Story
save.
of my life.
Yeah, so it couldn't save. Then I'm trying to, I do have the file, but I can't open it on my computer. So I sent it to the help desk. Hopefully they have replied. So I'm going to check their email and hopefully I can recover it. Okay. So let's say, looking at this coefficient, can someone tell me whether it's statistically significant or not? This is the intercept. Constant is the intercept. So how about, I'm gonna ask, Dan, are you here? Guys, where are you? You're here finally? I called you like a few minutes ago.
I couldn't find my mic.
Okay. So what do you think about the intercept of this model? The constant, do you think it's statistically significant under the 5%?
Talking about the t-score?
The t statistic, yeah.
Yeah. I think it's significant.
Why? What is your benchmark? Critical value under the 5%.
It's the 1.96, right?
Yes, exactly. So it's every time, guys, like every time I'm saying 5%, then it's always 196. So when I look here, this one in absolute terms, or even in like without absolute terms, it's less than the negative 196. It's greater than 196. So both of these are statistically significant. Okay. What about the p-value? You can actually read it in a different way. There is a 0% probability that the null is true. There is a 0% probability that student-teacher ratio, or the coefficient of student-teacher ratio, is equal to 0. In other words, statistically significant. Can you get that? Based on the p-value, how can you read the statistical significance? So 0 means 0%. Like, I want you to understand that the p-value is the probability under the null. It's the probability of the null. So if the null hypothesis saying that STR, or the coefficient of STR, is equal to 0, and there is a 0 probability that this is true, then this is good news. Do you understand that?
Yes.
Okay, how about the rest? Part, Dan, Lewis?
Yeah, I understand.
Okay. We can also use the confidence interval to check on our statistical significance. As long as the confidence interval does not have the 0, which is the 0 under the null, which is, we're saying that the coefficient of STR is equal to 0. I don't see the 0 here. It's negative, negative. I don't see the 0 here. It's positive and positive. They are away from the 0. So again, they are statistically significant. So either I depend on the T, P, confidence interval, I get the same answer, right? In Stata, it's easy because the T and the P and the confidence interval are reported for you. You don't have to compute anything. But if you have to do it by hand, then definitely the T statistic is the easiest, because it's not the easiest, it's the first step, because once I get this, I can compute the P. So the P is the second step after the T. Please stop me if you have any question. Let us see what's the rest on this table. So SS model, it's the SSE or the ESS, explained sum square. This is the numerator of the R square. SSR, right? It's the numerator of the standard error of the regression. TSS, total sum squared. So we have ESS, SSR, TSS. These are the degrees of freedom, and these are the mean squared. So if you divide this by this, you get this. Divide this by this, you get this, and so on. This by this, you get this. Number of observations, 420. What about the F statistic? So the F statistic is degrees of freedom of the numerator, how many coefficients I have in this model. I have only 1K, right? N minus K minus 1. N for 20 minus K, which is I just have 1, minus 1 for the intercept. So N minus 2 for 18. 22.58 F statistic. Do you think it's statistically significant or not?
You said 22.58.
Mm-hmm. Remember the table I showed you where I have the infinity?
Yes.
Remember that I told you anytime I have a sample size greater than 120, go to the infinity line?
Mm-hmm.
So this is exactly where we will be looking for a critical value. I need a critical value for a numerator of 1. So it's a first column, infinity line. So under the 5%, you're like, you choose 5, you choose 1%, you choose 10%, whatever. Actually, this number is greater than 3. Again, was it 3? No, it's not 3. Wait. It's not 3. It's the first column. I'm going to check it right now. Okay, it's 3.84. The first column with the infinity line, it's 3.84. So anyways, this number is huge, right? It's bigger than 3.84. So again, I'm the rejection region. I'm rejecting the null that this coefficient is equal to 0. The model is statistically significant. Again, it's saying the same thing. There is a 0 probability that the effect of STR on teacher score is equal to 0. Significant. What about this one? This one is telling me that there is only 5.12% explanation of the model. It's very, very small. And adjusted R square is not exactly the same, right? It's very, very close because the sample size is high. And this is the root mean squared error, which is based on the formula I gave you, which is the square root of SSR on the sample size, which is, if you compute the square root of, this is SSR. If you take this one, you divide it by N, you divide it by 420, get the square root, you will get this number. Okay. I'm gonna stop here. It's 420 or 320 already. Do you have any questions?
For the practice of data in Sakai, do we have to submit the do file?
You mean the do file of the practice?
Yeah.
You know what? It was there and I removed it because I want you guys to practice. So what I want you to do from today until next week, practice it, watch my videos on week 3, try to do it, okay? Because I don't want you to open my do file and see the answers right away. So practice it until next week and then I will post it for you.
But do we have to submit our own do file?
For what, the practice?
Yeah.
No, it's non-graded unless I ask you to do it for extra credit. Okay. So how about this? How about you guys do the practice question under week 3, which is this week, and then I will take it as an extra credit for 3 points for the midterm. Okay. So once you do that, I'm going to send you an announcement for that, so that if someone is not attending today's class, then you have it, the information. So once you do it, just in this case, yes, upload your do unlock file for me to check it, to give you the extra credit. Okay.
Is there any way you can open the getting started quiz on Pearson Lab?
Yeah, that's not a problem. Yeah.
Yeah, I missed that one because I signed up for Pearson Lab a little late.
Yeah, this one is okay, no problem. This one is just to take you through the steps on how to submit a quiz and so on, with like
Are any of those like
random questions, and it's not graded, but it's important.
What about the other one? I think it was like I'll tell you exactly what it said. Sorry, just one sec.
Mm-hmm. Okay, guys, if anyone doesn't have any question, can leave. If you have any questions, you can stay. I'll answer.
Sorry, my computer's just being a little slow right now, opening it up.
Mm-hmm.
You said we were all done for today, Miss?
Yes, we're done for today, and I'll send you an announcement about extra credit, and what else? Yeah, and that's it.
Okay, sounds good. Thank you.
Yeah, and if you have any question, you can post on the discussion forum, like while you're working on the do file.
Mm-hmm.
Okay, so I get a notification on my phone, and I'll log in and answer your question.
Oh, so I'm guessing like the get started homework and the get started quiz are both the same thing. They just kind of show you how to submit. They don't have anything to do with the actual course or anything like that.
No, it has nothing to do with your grade. It's non-graded. It's just like some students are new to my lab, so I want to make sure that they know how to go to the link, see where is the quiz, know how to submit. You know, it's non-graded. If you're comfortable with my lab, then you don't have to worry. I can open it anyways.
No, I'm comfortable with my lab. I just thought it was a grade, and I was like, oh, I didn't really want to start off on a bad note like that.
Yeah.
Since it's not a grade, now I'm 100% comfortable in my lab. I use it almost all the time, so I'm good.
Okay, that's perfect. Okay.
Right.
Any other question?
No, that's all for now, Professor. Thank you so much.
Thank you, Osman. Thank you.
Have a good one.
You too. Thank you.